Today I'm going to talk about high frequency solutions in Gaussian beams. Okay, and these are very, very useful solutions because they approximate, but yet they offer great physical insight. They are especially useful in the optical regime where the wavelengths are very short. Okay? So the first thing you can make when the wavelength is very short is called a tangent plane approximation. In the tangent plane approximation, you assume that a wave is locally tangent to a surface. So you can say that this is a tangent. This is usually called tangent to a surface. And if the wave is locally tangent, then you can more or less assume that the surface is flat, just like many of us thought that the surface of the Earth is actually flat because the radius of curvature is so huge that we don't know that the Earth is actually very, very curved. If you look from far away, it looks like a sphere. And so when the frequency is high, you can make these tangent plane approximations. And this is especially true when the frequency is high or the wavelengths go to zero and the frequency is high. Then you can apply what is called a local Snell's law. To assume that things are locally flat and this kind of thing is actually done a lot in the movie industry. For instance, if you have very, very complicated objects in a room, and instead of solving this problem approximately or exactly using computers, you can actually make tangent plane approximation and do ray tracing. Okay, this is called ray tracing. In other words, you assume that the plane wave becomes a ray. And as the plane wave bounces around in a very complicated environment, it behaves like a light ray. And you can trace the light ray and figure out how things should be looking like in a room. This is done a lot in the movie industry. To make things look realistic. Okay, so I might have a picture of that somewhere. Let me see. If I were to show it to you, then let me see. There's a problem advancing the thing. Yeah, this is the consequence of ray tracing. And by doing ray tracing, you can make things look very realistic in the picture. Okay, and as you can see, this is an important part of the movie industry these days. Let's try to go beyond ray tracing. One of the obvious things that you can do about ray tracing is actually to do lens optics. Let me pull this back again. And in lens optics, you just assume that if you have an object, it gives out light rays, and you can trace the light ray as they go through a dielectric object. And you can apply local Snell's law. And you can even use Fresnel coefficient to estimate the amount of transmitted light. And you can actually figure out the intensity of light here using ray tracing technique. And this is done a lot in the movie industry, as I mentioned to you before. And this is usually used if if this object is of size d, and if lambda is much less than the size of the object, then you can make the short wavelength approximation, which is also called a geometrical optics approximation. Sometimes called GOA in short, or just GO in short. Okay. You can actually figure out refraction and transmission quite easily in this kind of thing. And one of the other things I like to talk about is actually Fermat's principle. Fermat's principle is formulated around the 1600s for ray optics. And I like to point out the fact that Snell's law is also known in the Islamic world about 984 AD in the Islamic world. Okay, so what is Fermat's principle? Is a principle based on least action. It says the fact that if I have a very complicated object, if I have a light ray, okay, you have a source, you have a ray, the ray is going to bounce around, or maybe in this manner. I'm just drawing a cartoon picture, and it takes the minimum time delay. So in other words, if you were to send a pulse from a source to the observation point O, the time it takes to travel from point A to point O is minimal in terms of time travel if you were to make the optical pulse into a pulse. And time delay is also the same as minimum phase delay. Okay, I get the sign that my internet connection is not stable again. I'm going to switch on to another network in my home. Hopefully that I will get more stable connection. You're going to be disconnected temporarily when I switch over to another network. Okay, I hope that the stable connection is with us now, that I wouldn't get this warning message that my internet connection is unstable. Anyhow, so, you know, a time delay in the time domain is the same as a phase delay in the frequency domain. So when you have a pulse that can travel with minimum time delay from point A to point O, you can also show that it corresponds to a pulse that travels with a minimum phase delay. And that is the principle of least action, okay? And nature has it that nature is very efficient. Nature always does thing with the least fast. And with the least fast in the sense that when you travel from A to O, the phase is actually minimized. I don't know how nature does it, but nature seems to know that, and people in the 1600 knew about this, and they formulate the principle of least action to describe many physical interactions. Okay, so how do we use this Fermat's principle to solve problems that are related to lens optics? You can do it this way. We can actually arrive at what is known as generalized Snell's law quite easily by assuming that you have a point A, B, and C, and they are connected by light rays. Light rays can be thought of as plane waves. Okay, this is a light ray. And you can have another one here. And you can think of them as being locally plane wave or local plane wave. Because you can think of a source. If the source is producing a wave, it produces a spherical wave. Okay, you can think of this as a source. And when you have a spherical wave, if you observe at this point, you essentially see a local plane wave. A local plane wave is just a light ray. So when you see a locally plane wave traveling to you from a point source, which is actually in terms of a spherical wave, you can call that a light ray. And then the phase delay that it gets from A to B can be written down rather easily. And then the phase delay from B to C can be written down also rather easily. And we can write down those phase delays, and let me write them down for you next. Okay. So based on this picture, the time delay or the phase delay which is also the same as time delay, would be P, let me call that P. The P will be the phase delay, which is the product between the K vector in the incident ray times this vector R sub I. Okay, that will give you the phase shift of this wave as it travels from A to B. And then as it travels from B to C, it will suffer or accumulate another phase delay, and that phase delay is given by KT dot RT. KT is this vector over here, as you can see. RT is this position vector, and this will be the total phase delay. And let's assume that I'm going to change Xi a little bit. Okay, I'm going to change Xi a little bit. And if you go back to this picture, I change Xi a little bit. And if this is the minimum point for phase delay, it would be a stationary point, which means that if I were to change Xi a little bit, there's no change in the total phase delay, because by Fermat's principle, it will find the path with the minimum phase delay, and hence it's a stationary point. Okay, so the path of minimum phase delay is a stationary point. So if I were to find the change in the phase with respect to Xi, it should be 0 because it is a stationary point. And then now you can write this out explicitly. Okay, you can write this out explicitly. Then you can actually show that P as a function of X will be KIX XI, okay, for this part, and then the other one will be KTX XT, okay, and we say that ZI remains constant. ZI is constant. So if you look at this formula from this picture, if I were to change Xi a little bit, ZI remains constant. So I need to change the variation of P with respect to Xi only, since ZI does not change. ZI is in there, but I'm going to leave them out. Okay, so I finally, when I differentiate this, I get the fact that Xt, as you know, Xt plus Xi is a constant in this picture. If you look at this picture, Xi plus Xt is a constant. So when Xi changes, Xt changes also by the negative amount. So if I were to differentiate this with respect to Xi, then I will get KIX. But the second term, I will get KTX because Xt plus Xi is a constant. And so I have this, by Fermat's principle, KIX must be equal to KTX. And this is just Snell's law, that the x component of these two k vectors should be the same. Okay, this is just phase matching or Snell's law. Or Snell's law. So this is a wonderful result because it's obtained not using phase matching, but with the argument that the phase delay or the time delay between the point A to C should be minimized. Okay, and if you write this out in terms of angle, it will be Ki sine theta I would be equal to Kt sine theta T. Okay, this is what phase matching says, and it's just what we know as Snell's law. So are there any questions regarding the use of Fermat's principle? Okay, so this is wonderful news. It says that in the high frequency regime, when we can think of this as rays, we can write down the solutions rather simply, and we can use this concept to design meta surfaces. Just imagine that you have a surface here where you can affect the phase change on this surface. You can actually cause the light ray to have negative reflection when the light ray comes in this way because of this new Fermat's principle or Snell's law. We can get the light ray to bend this way. And at the second interface, it will just follow the ordinary Snell's law and bend this way. Okay, let's see how this is done. Okay, so this work was actually done by Federico Capasso of Harvard, and you can read about his work, which is pretty well known in the community. So instead of saying that the phase delay now is just the simple Ki dot Ri plus Kt dot Rt, okay, that we have a phase screen. Let's call this a phase screen. And it's made from meta surfaces. It's made from meta surfaces so that when the light ray goes through this phase screen, depending on where you are, the phase shift gained by the wave is position dependent. It depends on where you hit the phase screen, how the light ray hits the phase screen. And so what you have is something rather interesting, that you have a light ray, it comes in with Ki, okay? But then there is a phase screen that causes the light ray to add an additional phase due to where the light ray is hitting that surface. The light ray can be thought of as a local plane wave. And this kind of problems are usually not solvable in closed form. You can actually solve this problem using numerical software, using the field called computational electromagnetics. We'll learn about computational electromagnetics later on in the course. Essentially, it says that given Maxwell's equations, no matter how complicated the geometry is, we can solve Maxwell's equations with respect to this kind of very complicated geometry. Hence, we can send a plane wave coming into this geometry and study the phase shift of the plane wave as it goes through this phase screen and actually ascertain what this phase function should be. And the wonderful thing is that light ray has a, like if you take blue light, like your blue disk or blue laser disk, the wavelength is about 400 to 500 nanometers. But nowadays, nanofabrication is so wonderful. For instance, we can make transistors. They are about 10 nanometer in size now. Okay, so we can make a lot of wonderful things that are very, very small, much smaller than the wavelength of light. And if you work in an expensive lab, you can do nanofabrication. I believe our Berg Nanotechnology Center has that capability. You can fabricate this kind of tiny structures, made of maybe gold or silver or some other metallic structure on top of a surface. And hence you can think of this as being sub-wavelengths, very much smaller than the wavelength. And you can think of them as behaving like a phase screen. You can solve this problem with computational electromagnetics. So if this is your new equation for phase, then what you have is that according to Fermat's principle, then if the light ray is hitting the surface correctly, then you will get Kxi, Kix minus Ktx. And then there will be an additional contribution from the phase screen now. And all those have to add up to 0 according to Fermat's principle. If that point of interception is the point of minimum phase delay. Okay, so you can use this kind of things to do wonderful things like a flat lens, because you can actually get negative refraction if you have a source here, and if you have a meta surface, you can get the light ray to suffer negative or to go through negative refraction, and this is your new focus. And this is the source. Okay. Hence, you can make lenses that are very, very thin using meta surfaces. Okay, very, very thin lens. And if you're interested to find out more about this, you can visit with Professor Vlad Shalev. He's doing research in this area. So is I find remembering her name a little bit difficult. Alessandra Botashiva, I think. I'm not sure about the spelling. Okay, they're in the nanotechnology lab in Berg Nanotechnology Center, and you can talk to them. Okay, and this is what gave rise to what we call the generalized Snell's law. Okay, because of this additional term we have over here. Okay, so are there any questions regarding this? Well, if not, let me move on to talk a little bit more about computational electromagnetics, on how to solve this kind of problems involving very complicated geometry like this. And what you do in computational electromagnetics is to actually use periodic structure. It turns out that if you make all these things out of periodic structures, then the problem can be simplified. We don't know how to solve this problem in closed form. All the things that we have dealt with in this course assume no such structure. However, if we can use Bloch-Floquet theorem, you can actually solve for the scratching solution for such a structure. What it says is that once you have a wave coming in, the reflected wave is not just one single ray. What you have is actually the reflected ray is being spread out into multitudes of rays. Okay, so these are called Floquet mode. Instead of just a single mode. And then by solving this problem using Bloch-Floquet theorem, you can ascertain the phase shift. The phase shift as a function of x and y. That is, if I were to arrange these structures, and if they are arranged in a specific manner, what should the phase shift be? I can obtain the phase shift by solving this problem using computational electromagnetics, and then you can use some commercial software to solve this problem.